Assalamualaikum warahmatullahi wabarakatuh. So welcome to my video. So today, we will continue with chapter 8 on the topic of per unit system, and we have come to the example number 7 on this particular circuit. So this is a single line diagram, and the question asks you to determine the per unit values of the following single line diagram and draw the impedance diagram. So next, from the impedance diagram obtained, so calculate the terminal voltage of the synchronous machine. So this part, and then the transmission line current over here, the IL actual. Okay. Now, before we start with the analysis, so how we can actually understand the single line diagram. So this is again the generation side. So we have our generator over here, all right, with the impedance of 50%, the apparent power as 50 MVA. All right, this is the bus bar, and then we move to the transformer number 1 with impedance of 0.1 pu. So here again, the value of apparent power, the S, the power rating of the transformer, as well as the voltage ratio. And then from here, frankly, we can see this is actually a step down transformer. Okay, and then move to the transmission line. So in between, let's say we have bus bar number 1, bus bar number 2, bus bar number 3, as well as bus bar number 4. So in between these two bus bar 2 and 3, so we do have the transmission line. Right? And also the impedance of the transmission line provided in this question. And then as we move to transformer 2, right, impedance is given here 0.04 pu, as well as the S and the voltage ratio, which is the step down operation of transformer. Okay, this is bus bar number 4, and then the area of load. Okay, so this is the real power, the actual power given by 40 megawatt, as well as the power factor. Okay, the cos theta. Okay, which is 0.8 power factor lagging. Right. So this is how we can understand the information provided in the single line diagram. Okay. And of course, we can actually divide into several zones. Okay, let's say I draw a dotted line over here. So I come down to this line, this vertical line, for example, for zone number 1. Okay, and then this dotted line again come down to this line, this vertical line. So this is zone number 2. Okay, in between transformers. Okay, so this is zone number 1 between the generator to the first transformer. So between transformer number 1 up to transformer number 2, so we consider this as zone 2. And then zone number 3 covers the area between, sorry, this is not here, but this one is here. Okay, so this is here. Okay, should clear this one. So never mind. So here to here actually. Okay, this is the number 3. Okay, cancel this one and cancel this. Okay. So in between transformer 2 and transformer 1. Okay. This is T2, this is T1, this is the generator, okay, or the synchronous machine, and this is the load. Okay. All this is having the S base and Z base respectively. Okay. So this is implemented here, here, and here. Zone number 1, zone number 2, as well as zone number 3. Okay. So this is the basic idea on how we should start with the solution. So step number 1, divide the power system into different zones. So they have seen this. So we have zone number 1. Okay, we have zone number 2, as well as zone number 3. Okay, so if I can write or plot the dotted line, okay, you can see a clearer picture, okay, of the zone division. Okay, and then choose common base MVA and base voltage for each zone. So typically for this type of SLD, so we pick 100 MVA, for example. Okay, this is due to the easier calculation later, because we just have a simple number of 100. Okay, so this value 100 MVA is picked as the S base. And then the V base, of course, dependent on the zone of the transformer. Okay, let's say this is 275. Okay, zone 1. So this is the rating voltage. So we pick 275 for zone number 1, the Z base. And then this 132, zone 2. So this is Z base. Sorry, this is not Z but B base 2. Okay, so this is B base 1. And then okay, this is 132. Again, V base 2, and this is 63, come the V base 3. So let S base 1 equal to S base 2 equal to S base 3, 100 MVA. Okay, and then VS1, so we have seen this value. So we have picked this value, and 66 kV is this selected value in zone number 3. So calculate new impedance base for all zones. So S base 1. So we have V base 1 square over S base 1. Similarly for S base 2, so we have V base 2 square over S base 2. Okay. Similar process goes to V base 3 square and over S base 3. Again, substitute all the value, 275 from here right to here. This value number 2, base number 2 here, and base number 3 here. Okay. With identical value of S base. Okay. S1, S2, S3 as per defined here. Right. This 100 MVA, 100 mega volt ampere. So this is the new base value for Z1. So new base value for Z2 and new base value for Z3. Step number 3, calculate new current base for each zone. Again, so you must be familiar with this equation. Alright, so this equation. Alright, and this is similar, the same equation actually. Okay. So I base equal to S base over square root 3 V base. Okay, we have base number 1, number 2, as well as number 3. So substitute the value of S, which is 100 MVA just now. 100 MVA, 100 MVA, square root 3. So remain same to all equation, but we come to V base. Now we have its respective value. Okay, 125, 175, 132 as well as 66 kV. Okay, now come the I base 1, I base 2, and I base 3. So done with the Z base, new Z base. So we have done with I base. So now step number 4, we convert all impedance to new bases. So we have ZG, so ZG generator impedance. The new, so we have the old, which is provided in question or in the system. So we have this equation, V old over V new, square it, then multiply by S base new over S base old. So normally we have no problem with the base, the V base, or the V, whether it is an old or new. So basically we have the same value, but once we come to S, so there is difference between new and old. So 100 MVA is considered as new value from what we have picked earlier. So this is the rating value in the SLD or the single line diagram. So 100 MVA over 60 MVA. So this is, if you remember, this is the S base we pick. Okay. So this is the S rating for this equipment, right? For generator especially. And then complete the calculation. ZG new is giving J0.32 pu. Okay, now we move to ZT1, so transformer 1 impedance, okay, and also transformer 2 impedance, the new value. So we have the old impedance J0.1. I believe this is taken from question. This one also J0.04. So this is divided in question, considered as an old value. So we have no issue basically for V, the voltage. For V voltage, regardless the old or new. So since we have picked the rating value of the transformer as the base value, so basically this old and new so are similar. Okay. So S base new over S base old. So now it depends on the rating power of the equipment. Okay. So we pick again this one as the base new, and this is from the power rating of this particular equipment. Similarly, for transformer number 2, so we have S base new over S base old. So this is from what we have picked earlier. So this is the power rating, okay, the rated power of the transformer 2. So it's J0.01 pu for the first transformer, and then J0.08 pu for the second transformer. So transmission line per unit impedance on 100 MVA and 132 kV base. So this is for the transmission line. TL stands for transmission line pu. So we have ZT actual. So this is initially equal to ZT actual over ZT base. Alright. So ZTL base actually. So ZTL, meanwhile, ZTL base, okay, is equal to S, not S, but we have V base, okay, square over S base. Okay. So since transmission line is located in zone number 2, so this caption or the notation supposed to be 2, or here V base 2 and S base 2. Okay. So ZT actual over ZT base 2 over here. Okay, here. So substitute into this and then rearrange. Okay, multiply by S base 2, okay, over V base 2 squared. It's coming from here. Okay. So substitute the value of ZT actual J 3.48 and then the S base 2 as well as the V base 2 and square it. So now the final value of ZTPU is 0.02 PU. So step number 5, find per unit load voltage. So the given load power factor, which is cos theta, 0.8 leading. So therefore, so arc cos 0.8, so in degree giving 36.87 degree. Okay. So how about the per unit load voltage? So again, VLPU, VL actual over VS, V base 3. Okay. So remember, 3 reflects the load zone. Okay. So this is where the location of load zone number 3. Okay. 36 over 66 kV. You can see from the SLD over here. So this is the load zone. Okay, zone number 3. So we pick the V base 3 here according to the transformer voltage rating, which is 66 kV here. The one I round, the one I circle over here. Okay, which is 66 kV. Okay. Now the actual, which is 66 kV over the base analytical value 66 kV. So the final value of VLPU is 1.0 P. Okay, so taking load voltage as reference, so we can actually simply write that VLPU equal to 1.0 degree of the phase angle. So step number 6, find per unit complex load power. So this is the equation again. So we have P equal to S over PF, or similarly we can write down P equal to S over cos theta, right? So this is actually the another alternative. We can calculate power according to S and power factor. Okay. So P real power, again, if you see in your diagram, it is provided over there. It is 40 megawatt over 0.8 power factor, and giving us the apparent load as L 50 mega VA. All right, here. Okay, so maybe in short we can write like this: 50 M VA L. So for leading load, so we can write complex load power as L actual. So as L, so this is the symbol of theta. So this is equal to 50 to the 10 multiplied by 10 to the power of 6. Okay, MVA. So this is positive angle due to the leading load. Okay, so therefore per unit complex load power as LPU, this is equal to SL actual over S base 3. Remember, S base 3 is coming from the load zone. Okay, so zone number 3. So 50 here, MVA into here, and this is the base we picked earlier, which is 100. And then SLPU equal to 0.5. All right. So find per unit load current, IL. Okay, this is from Ohm's law. Basically, this is from Ohm's law. So IL equal to SL over V. So this is we just obtained, and then this is VL we have defined earlier. So giving LPU equal to 0.5, 36.87 PU. So find PU load impedance, ZL actual equal to Z line to line square over SL conjugate. Okay, so 50, again this is from here, all right. So from this calculation into here, and then don't forget the conjugate operation. So Okay, so okay, here when transform it into equation or into value, so it must give negative value instead of positive. Okay, the inversion from the previous signage. Negative, and then VLL of zone number 3 is 66 kV. You may refer back to the SLD and zone number 3. Okay. Therefore, per unit load impedance, ZL PU ZL actual, okay, sorry, this is ZL actual 69.696 plus J 52.272 ohm. So, and then from there, the actual, okay, into here, and then divide by the base value on zone number 3, giving us the PU, the per unit load impedance. Okay, 1.6 plus J 1.2 PU. So then we have complete, okay, the impedance analysis, okay, especially the PU for each of the components. Okay, now step number 8, we draw the single diagram. So this is the SPU for the generation side or generator, synchronous machine. So we have its impedance ZG. So this is transformer number 1. So this is the transmission line impedance. So transformer number 2 impedance. So this is the I load, the load current PU, as well as the impedance load PU. So total up everything, okay, this plus ZG plus ZT1 plus ZTL plus ZT2, that's one number 1, and plus the load impedance PU. And then the total giving us 2.349, 47.07 ohm. So per unit source voltage, VSPU, I load PU multiplied by Z total. Okay, so this is what we have calculated in this previous slide over here. Okay, the ILPU. Okay, take it and put in this equation. Okay, so this is from previous slide, and this is the final VSP PU. Okay. Alright, therefore, actual voltage supplied by generator. So we have calculated the VSPU multiplied by the base 1 in order to get the actual. Alright, so this is actual voltage. So in zone number 1, so the base is 275 kV. So this is the final value of actual voltage supplied by generator. So how about the per unit transmission line current? So since our equivalent impedance circuit over here is connected in series, so we can say, so all in series. So we can say that the transmission line PU, this is equal to load current PU equal to 0.536.87 PU. Okay, actual transmission line. So since we have the PU value over here, so multiply by the base, okay, number 2, because transmission line again is located in zone number 2. All right, so pick the base current in zone number 2, which is 437.387 multiplied by ITL, and giving this value to 118.669. Right, it's supposed to be positive, so we delete it. Okay, the IL here, IL come from here, and then ITL is here. Okay, it's supposed to be negative sign over here. Okay, this is correct answer. So what example 8.0, find the real and reactive power supplied by the generator. So now we have to calculate the real power, okay, here supplied by the generator. Let's say we put G notation over here, okay, as well as the reactive power Q of G Okay, right, in this SLD diagram. So similarly, so we have three different zones: zone number 1, zone number 2, and zone number 3. Okay, so this is looks familiar to what we have analyzed in example 7.7.0. Okay, so let system MVA equal to 100. So we pick again the S value, okay, which is base value of S, okay, 100 MVA. Zone number 1, 100 MVA. So base number 1, 20 kilowatt is from here. Okay, from here as well as from here. Okay, so for this is the V, or the base voltage for zone number 1. So 132 for zone number 2, and 11 kV here for zone number 3. I mean for the base voltage. So base current I base square root IS base over square root 3 V base. So 100 MVA over square root 3, 20 kilowatt. Okay. And base impedance Z base 1. So V base square over S base 1, 20 square over 100 multiplied by 10 to the power of 6. Okay, 100 MVA, 4 ohms for the Z base 1. So generators per unit impedance of 100 MVA. So this is ZG 0.1 PU is from here. Okay, just divided by 100. Okay, giving us the value of ZG G 0.1 PU, and then this is directly taken from here. Okay, again divide by 100. Okay, for the T1 PU. Okay, so we have done analyzing the base value, the Z, especially in zone number 1. Okay, so now we move to zone number 2. So this is again the base, and I believe we have picked this 100 MVA as the S base, V base. So this is the transmission line impedance, right? And as well as the 132 over here, the V base in this particular zone number 2. Okay, 100 and 132 kV. So base current again for the second zone, or zone number 2. So we have V base over here, 132. Okay, the rest are similar to what we have seen earlier. Okay, this is I base 2. So what about the the base impedance, V base 2? So Z base 2, sorry. Okay, V base 2 square over S base 2. So 132 now. kV square root over 100 MVA, 174.24 ohms. The transmission line per unit impedance on 100 MVA base. So V line PU actual over base 2. Okay, located in zone number 2. So line, this is directly taken from question. Okay, and then this is the Z base 2. We just calculate over here. Okay, into here. Okay. So this is again, if you can cross check, here is the value of Z line actual. Okay, actual. So zone number 3, same still with the same value of MVA, 100. So the base is different now. We pick 11 kV. Again, try to calculate the I base. Okay, we have 100 over square root 3 and 11 kVA from here into here. Okay. And then IL actual, so this is actually from P load equation. Okay, so we have all in line. Okay, we have VLL, line to line value, we have I line, okay, cos theta, which is the power factor. So rearrange in terms of IL actual, so we have P load over square root 3 multiplied by VLL power factor 40 megawatt. I believe this is again provided in the question. So we have square root 3, the VLL 11 kV. Okay, this one, this number 3 is similar to VLL, and then this is the power factor from the question. Okay. So IL actual 2624 ampere. Therefore, per unit load current, so ILPU, IL actual over I base 3. Okay, I actual over I base 3. Okay, so here is the keyword of the negative sign of the phase angle. Okay, I mean lagging condition of the power factor. Okay, so lagging, we just simply put a negative sign over here. Okay, and divide by I base 3. So this is your value of IL, PU 0.5 negative 36.87. Then from there, per unit load current, so we have VL, so this is the load current, this is V actually. Alright, so this is correction, this is rotation. So similar process from what we have seen in example 7. So 11 kV over 11 kV, the actual over the base. Okay, now giving us 1.0 zero phase angle PU. So now per unit transformer TU impedance of 100 MVA base. So since we have picked 100 MVA as a new, so we have to calculate the new impedance of transformer 2. So all impedance transformer 2 multiplied by V base O square over V base new square multiplied by S base new S base all. Okay. Again, so we have no problem with this value. Okay, basically we have 1 over here. 11 over 11. So we have 100 as a new S value, and then this is the old rating power of a transformer 2. Okay. So having that all values, now we come to the per unit equivalent circuit. So now we can plot the power or the impedance equivalent circuit. So J 0.1, this is for the ZG. Okay. Oops, this is for the ZG. Okay. And then this is transformer number 1. Okay, this is impedance for transmission line. Okay, this is Z for transmission number 2. Okay, and also the load current and the load voltage PU, all in PU, right? So apply conservation of P and Q. So per unit active power consumed by transmission line. So this is transmission line feeder. Okay, this is another term we can use to represent transmission line. So we have our equation over here, P equal to I square R feeder PU. So where to get R here, we can see, okay, for 0.04 from this value. All right. So this is, remember, the transmission line PU. So this is R, okay, value, okay, 0.046. Oops. Okay, into here. 0.046. So you see, this is the magnitude of the I load, okay, or I P load P PU. So just the magnitude value. So giving the transmission power consumed or the feeder equal to 0.0115 PU. So what about the actual? So just multiply by S base 2. Okay. S base 2, you multiply by S base 2. From there you can get So this is 100 MVA. You can get the actual active power consumed by transmission line, which is 1.15 megawatt. And this is PTN. So total PU active power, P, supplied by generator, we have the transmission line or the feeder plus the P load. Okay. So we have 0.115 plus 0.4. This is for P, this is for PPU. So for the load P, okay, so again, here we can see from here, this one, okay. So the P load PU, okay. So we have here the P actual, okay. So we have seen this formula in the previous example number 7.0. So this is actually power factor. Okay. And then we try to calculate. Oops, where it goes? Over here. And oh, sorry, this is not power factor, but you can calculate from P and so this is equal to P actual divided by S base. Okay, so the P actual just now is 40 megawatt. Right, divided by S base. Oh, S base. Let me write in full. This is 100 MVA. And then here equal to 0.4 PU. Okay. And then only we can calculate the active power supplied by generator 0.4115 PU. So total actual active power supplied by generator, again, this is the PU value multiplied by S base, okay, which is 100. And the per unit reactive power consumed by load, so QL load equal to S load PU square over P load PU square. This is from power triangle. Okay, let me draw for you the power triangle. So this is theta. Okay, so we have S over here. So we have P and we have Q. So the relationship between these three, S square equal to P square plus Q square. So rearrange, let me write down here. So we have Q square equal to S square minus P square. So n square Q, we get here square root S square minus P square. Alright. And S load PU is given by 0.5 squared minus 0.4 squared for the P load PU. Okay, so 0.3 is the answer for Q load PU. And then from there, before we go for further analysis, so we try to calculate the total distribution reactance or the Z total PU. Okay, all the impedance value we have over here again, okay, into this equation, and then giving us J 0.53U ohms. So per unit reactive power consumed distribution system reactance, Q system, I square, this is from Ohm's law, I square PU multiplied by Z total PU. So this is what we have obtained earlier. Okay, so giving Q system 0.133 P. So what about the generator? So the total reactive power PU supplied by generator, we have a key system plus Q load PU. All right, so we have seen here the Q load PU 0.3 PU, so we have also the Q system. Okay, so for the overall Q coding to the Z total. Okay, and then from there, so we might able to get the value or the total PU reactive power supplied by generator. And then from there, we just multiply by S base 1. Okay, the location of the generator, remember, is in the zone number 1. So you multiply by base 1, okay, these two, so giving us the actual reactive power supplied by generator, okay, for 3.3 megawatt. So thank you very much for your attention, and sorry. So I'll see you later on the following topic. So enjoy the video. Again, thank you very much.